Hi, and welcome to today's presentation. It's focused on the topic of homeostasis. The term homeostasis is derived from two Greek words, homeo, which means unchanging, and stasis, which means standing. In its simplest form, it means staying the same or keeping the internal environment in a steady state. Okay, so homeostasis in physiology, again, which literally means to stay the same, is regarded by many as the fundamental concept in both physiology and medicine. Every day, the external environment changes in many ways, such as shift in temperature, changes in humidity, pollution, nutrient levels, fluctuation of blood sugars, and exposure to pathogens. These changes can threaten our health, but our bodies respond to keep our internal environment stable. This process known as homeostasis, which ensure that vital functions like blood pressure, glucose level, pH balance, carbon dioxide concentration, and body temperature stays within healthy ranges of optimal performance. Now, the concept was first investigated by French physiologist Claude Bernard in 1849. However, it was Walter Branford Cannon who coined the term homeostasis in 1926 to expand on Claude Bernard's concept of internal environment. Now, how does the body maintains this balance? No matter what variable is being maintained, all homeostatic system consists of three main parts: a receptor that detects a stimulus, a control center that processes the information, and an effector organ that carries out the response to achieve the desired effect. Basically, there are two types of feedback loop: the negative and the positive. On your left, a negative feedback loop maintains internal stability by sensing changes away from the normal levels and initiating response to correct them. For instance, when body temperature rises, cooling processes are triggered until balance is regained, after which these responses are halted to keep the internal environment stable. While positive feedback on your right amplifies a change in the body to reach a specific outcome. For instance, during childbirth, pressure on the cervix triggers oxytocin release, which strengthen contraction. This contraction then stimulate more oxytocin, creating a loop that continues until the baby is delivered and the cycle ends. Now, in these slides, it provides additional examples of both negative and positive feedback loops. Included here is on top the fluctuation of blood glucose, which will be explored in the more detail in the upcoming slides. Now, in a big picture, the negative feedback loop in glucose homeostasis works by detecting high blood sugar, prompting insulin release, which helps cells absorb glucose and return levels to normal. However, there are dual negative feedback loops for glucose homeostasis, one for hyperglycemia and one for hypoglycemia. In hyperglycemia on your left, the trigger is elevated blood glucose levels, such as after a meal. The beta cells of the pancreas acts as a sensor and control center, releasing insulin in response. Insulin then acts on skeletal muscles and adipose tissue, promoting an uptake of glucose into these cells. This process lowers blood glucose level, completing a negative feedback loop to restore balance. On your right, the negative feedback on hypoglycemia when blood glucose level fall. This is during fasting or exercise. The alpha cells in the pancreas detect this drop and respond to the by releasing glucagon, and glucagon then stimulate the liver to break down glycogen and produce new glucose through gluconeogenesis, increasing blood sugar level and restoring the balance through a negative feedback. The human needs a constant supply of energy to support vital function like brain activity, muscle work, and cellular maintenance. But since eating happens intermittently, the body maintains blood glucose level between meals through a precise regulation, a process called glucose homeostasis. Following a meal, the rise in blood glucose prompts the pancreas to secrete insulin, which helps cells absorb glucose and its storage as glycogen to reduce blood sugar. Any excess glucose is converted into fat and triglycerides in adipose tissue, with a smaller portion converted into protein. In between meals or during fasting, failing glucose prompts glucagon release, signaling the liver to break down glycogen and release glucose to maintain energy. During prolonged fasting or stress, the body produces new glucose from other sources to keep blood sugar stable. So, protein is not strictly speaking a fuel reserve because protein molecule serves mainly as organ structures and function. But protein can be degraded from muscles and liver during starvation and other period of stress that provide amino acid substrate for gluconeogenesis. So the basic principles of fuel reserve in a healthy 70-kilogram man stores energy mainly as fat in the form of triglycerides, glycogen, and protein. Glycogen serves as a modest but rapidly available source of glucose that the body taps in between meals and during the night. In contrast, fat stores are vast and serve as the primary long-term energy source during fasting. If you look at the fuel reserve of fat calculated per kcal, a staggering reserve of 135,000 kcal compared to combined glycogen stored in the liver and muscle. That goes to show that fat in the form of triglycerides is the most efficient fuel storage in human. Now, protein is generally preserved but can be broken down for glucose production during prolonged fasting or stress. Now, this system ensures continuous energy availability despite intermittent eating. Now, adipose triglycerides are the body primary and most efficient energy stores, containing more calories per gram and much less water, and about 15% compared to the others stored like muscles, which hold around 80% water. This makes fat as a dense and compact fuel reserve. Skeletal muscles hold the largest amount of glycogen, but the liver is the main source that releases free glucose into the bloodstream. Liver glycogen plays a key role in maintaining blood glucose level during fasting. About one-third of the body protein can be broken down without causing any harm, but excessive protein breakdown for energy impairs important function. To protect protein, the body relies on fatty acid oxidation, ketogenesis as alternative fuel sources. Now that there are two principal circulating fuel in humans, glucose and free fatty acids. These are stored intracellularly as glycogen and triglycerides respectively. Protein again are not the body go-to fuel source. It's more of a structural priority, and carbohydrates are the body preferred fuel. Now, why amino acid aren't first choice or protein are not the body go-to fuel source? Number one is structural priority. Amino acids are needed for building and repairing tissues, making enzymes, hormones, and immune molecules, burning them for energy risk compromising these essential functions. Number two, there's no storage depot for protein. Unlike glycogen or fat, there's no protein tank. Using amino acid for energy means breaking down functional protein. Think muscle wasting during starvation or illness. And number three, metabolic costs. Converting amino acid into usable energy via gluconeogenesis or the Krebs cycle is metabolically quite expensive and slower than using carbs or fat. And lastly, nitrogen waste. Catabolizing amino acid produces a substance called nitrogenous waste, ammonia to urea, which must be excreted. This adds to a redox burden in the liver and kidney. These are poisonous materials or substance that should be properly metabolized and excreted. Now, when does the body use amino acids for fuel? Now, in starvation or prolonged fasting, once glycogen and fat are exhausted, the body resorts to muscle protein for glucose production via gluconeogenesis. In extreme endurance or cachexia, protein breakdown contributes to energy, often at the cost of muscle mass and functional integrity. In a physically active, well-nourished human, the liver draws energy from multiple sources, fatty acids, glucose, amino acids, and plays a central role in maintaining blood glucose. Muscle relies on both glucose and fat, adjusting fuel use based on activity level. The brain, however, depends almost exclusively on a constant supply of glucose, as it cannot store glycogen or use fatty acids directly, making it reliant on the liver for fuel. So, what are the hormonal regulators of fuel homeostasis? Number one, energy storage and release in the body are regulated by hormones, with insulin as the primary promoter of energy storage. Number two, counter-regulatory hormones like glucagon and catecholamine oppose insulin by stimulating processes such as glycogen breakdown, glucose production, fat breakdown, and ketone formation to release energy from the liver, adipose tissues, and muscle when it is needed. Now, plasma glucose levels are tightly controlled by hormones. Insulin, glucagon, and epinephrine acts quickly within minutes, while cortisol and growth hormone have longer effect over a period of hours. Normal blood glucose ranges from 3.8 to 7.0 millimoles or 70 to 140 milligrams per deciliter. The brain relies exclusively on glucose for energy, but it cannot produce glucose or again store glycogen. Now, fuel homeostasis in human. In human, excess fuel after eating on your left are stored mainly as glycogen and triglycerides with some protein reserve. On your left during starvation, or on your right rather, during starvation, these stores are broken down to supply energy to organs. The shift between storage and breakdown are controlled by changes in insulin and the counter-regulatory hormones. Now, glucose homeostasis aims to keep blood glucose level stable within narrow range through a balance action of insulin and these counter-regulatory hormones. Glucose concentration is more tightly regulated than any other fuel, while free fatty acids and ketone bodies are vary widely in the bloodstream. Okay, now we're ready to discuss the 5 phases of glucose homeostasis. Phase 1, which is the absorptive phase, that's 0 to 4 hours post-meal. Glucose originates from dietary carbohydrates absorbed in the intestine and most tissues, including muscles, adipose tissues, and liver, actively use glucose for energy as well as storage. The brain relies entirely on glucose as its primary fuel during this phase, with insulin facilitating uptake in the peripheral tissue. The next is phase 2, which is the post-absorptive phase. That's 4 to 16 hours after eating. Glucose is now derived from hepatic glycogenolysis, triggered by rising glucagon level. The liver exports glucose to maintain blood levels, while muscles and adipose tissues reduce their glucose uptake and begin shifting towards fatty acid oxidation. The brain continues to depend on glucose as its sole energy source. Now, phase 3, which is early starvation, 16 to 48 hours, glucose production shift to gluconeogenesis using substrates like lactate, alanine, and glycerol. The liver is primarily primary source with some contribution from the kidney. Glucose is prioritized for the brain, red blood cells, and adrenal medulla, while muscles and other tissues increasingly rely on fatty acid. The brain still uses glucose predominantly, though ketones production begins. Now, phase 4, the intermediate starvation, that's up to 5 days, 2 to 5 days. In the slides, you can see up to 16 days. Gluconeogenesis continues but slows. Ketone bodies produced by the liver and fatty acids becomes the significant fuel source. Glucose is now mainly used for tissues that cannot metabolize ketones, such as red blood cells. The brain begins to use ketone bodies, substantially reducing its glucose demand and sparing muscle protein. And the last phase is phase 5, which is prolonged starvation, more than 5 days. Glucose originates primarily from renal gluconeogenesis with minimal hepatic contribution. Most tissues rely on fatty acids or ketones, and glucose is preserved or reserved for obligate users like red blood cells. The brain's major fuel becomes ketone bodies, which can supply up to 60% of its energy needs, significantly reducing its need for glucose and allowing for significant protein conservation. Now, just to emphasize the contribution of the kidneys during the post-absorptive phase, typically overnight or between meals, the kidney plays a significant and often underappreciated role in maintaining blood glucose level to renal gluconeogenesis. Now here you can see that renal glycolysis and gluconeogenesis pathway and enzyme distribution. This section illustrates this distinct pathway of glycolysis and gluconeogenesis, highlighting how the kidney contribute to glucose metabolism during both fed and fasting state. The kidney uses glycolysis mainly in the renal medulla to generate energy under low oxygen condition, while gluconeogenesis occurs primarily in the renal cortex, especially in the proximal tubules, producing glucose during fasting or stress. Together, these processes help maintain blood glucose level and support the kidney energy needs. So, in summary, homeostasis is the body's way of maintaining stable internal conditions such as temperature, pH, blood pressure, and glucose despite external changes, ensuring that organs work properly. The body maintains blood glucose within a narrow range to support vital organs, especially the brain. After a meal or following a meal, insulin stores glucose as glycogen and fat. In between meals, glucagon and other hormones release glucose by breaking down glycogen, producing new glucose, and mobilizing fat. The liver and the kidney produces glucose for the body while muscle glycogen is used locally. This hormonal balance ensures steady energy and spares protein despite irregular eating. So thank you for listening. That's the last slide.